Lagler. He has a degree in geology from the University of São Paulo, a master's degree in geochemistry from USP. So please give your presentation, Mr. Bruno Lagler. Good afternoon, ladies and gentlemen. I believe that we are a little late. This presentation, in fact, is a history of how we arrived at some data that Mr. Sebastian has just shown previously in the previous presentation, and Lucas is going to give a presentation this afternoon about this data, how we try to revitalize this project that we started in 2019. So this is a brief summary of what I'm going to discuss. So I'm going to discuss phosphate sedimentary deposits, and Sebastian mentioned that this is part of our DNA in the production of fertilizers, and so we are based on phosphate deposits. Not all of you are well know these deposits very well, even though it doesn't have the same characteristics of the classic sedimentary deposits like we have in the USA and Africa. I'm gonna talk about the history behind the project, how we did it, the exploration in the past, how we changed everything in 2019, the papers and the work we did to revitalize the project, some results and the conclusions. So very briefly, in the phosphate sedimentary deposits, they are found in all of the continents, okay? And so they are more recent and they are more common, okay, from the Neoproterozoic period until now. And the thicker lines in the north of Africa, in the Pacific Ocean, in the USA, these phosphate in classic deposits of phosphate, okay, they are very, very recent when it comes to their geological history, okay? They are millions and millions of years old. And so it's about 600 million years ago, and that is a great difference between the deposits. So the world mineral reserves of phosphate, they are estimated in about 70 billion tons. About 95% are from the world reserves, okay? As sedimentary phosphate deposits. And in Brazil, we are a little different. And we have some phosphate sedimentary deposits arising or appearing in Brazil. Discussing the creation of these deposits, they are connected to the phosphorus cycle, okay? So in general, you have igneous and metamorphic and sedimentary rocks. Phosphate is present in all of them. So you have at least a little bit of phosphate in all of them. Erosion impacting these rocks releases particles of phosphates into nature. They are taken into the oceans by the rivers. And when there is a creation of sedimentary phosphate deposits, there is an activity, okay? So it's absorbed by ocean beings, and you have many processes, the decomposition of the organic matter, the reuse of the phosphorus by other beings, live beings that are at the bottom of the oceans, and then we have the reabsorption and rainfall, and then we have the deposit of phosphate. So if you analyze the Morocco deposits, the USA, the American deposit, we don't have stingrays, okay? And we only have microbiological. So you had this biological enriching that is some of the modern phosphate deposits they have. So the sedimentary deposit in Arraias, and so we have Bambuí, and so this is in the center part of Brazil, and the rocks that we find associated to them are dolomites, and we have the Santa Fe group there because this group was never associated to the phosphate deposits in Arraias. Arraias is a location in Brazil, and they can contribute a lot, and this changes many things when it comes to our mining operations. As I have shown before, in red in red, you can see the igneous granite deposits. And then when we have the San Francisco Basin in orange with the pink, between you can find the phosphate deposits from the Sete Lagoas Formation in the center of Brazil. Usually the sedimentary deposit in Arraias up until 2020, it had two main mineral types. So you have 90% of the deposit was made by these the clay and the sand here, and now it's about 5%. 10% of the volume of the deposit had phosphatic breaches. Okay, and these breaches, they are basically formed by tectonic efforts. Okay, and so you have the silt here, and there was a fracture and the recrystallization of these fractured areas or parts here. I'm going to talk about the history of the project. So the exploration started in 2018, and this is the project's main arrangement. Okay, in general, we have many mineral bodies there, the brown lines, you have different sizes, and around our beneficiation plants in the right hand side of the image. I'm not going to discuss all of our targets, our mining targets. I'm going to talk about mainly two: Domingos, which was the mine where we started our operations, and this was basically because of the distance between our plant and our mine in Coité, where we carried out the main studies at the time. And the mine there in Coitella was already opened, and the type of deposit, and this was done in the Coité mine, and it has different characteristics when it comes to the Domingos mine. Since we studied the Coité mine more than the Domingos mine, that's when we started having a few problems. In general, the exploration started in 2008, so we did the geological mapping. We also did the analysis in 2008. We studied 27,000 meters, and also we did the analysis and showing the two targets that I mentioned in the previous slide. In Coité, we had a distribution of holes, okay, between 60 and 40. So you have the adequate distribution of the holes for the analysis that we considered adequate. In the Domingos mine, okay, you had 41 holes. So the reverse analysis does not give you a complete sample, an entire sample. So if you want to characterize the different kinds of samples or samples, you can do that. It gives you a sample that is diluted. So you have similar ores, similar minerals. So it depends on the size of the particles or in the color. Sometimes you cannot separate this unless you have deep knowledge of this. In the Domingos mine, they still didn't have this level of knowledge. So in 2013, we issued our technical report. We analyzed 79 million tons with an average content of 5%, and if you compare that with the classic deposits of phosphate, it's not so different. Yes, if we get the deposits from Morocco, yeah, and so it's about 20%. So it is a sedimentary deposit, but some of the characteristics are way more challenging for us. So we operated from 2013 to 2019 based on these premises, and we started identifying some problems. Up until 2019, we didn't get all the recoveries we needed, and we had to stop our operations. And we asked ourselves, what went wrong? What could we do to make things right? And at this moment was when we thought about the main problems, and then we identified that the geological mapping, we identified only two types of ores. But when we opened the mine, we identified at least 5 types of minerals. Okay? So besides the analysis methodology that we used in the Domingos mine, which was not the correct one, we couldn't get a geological model that was extremely accurate and precise. Our content of P2O5 And where is the P2O5? It was not very consistent, the information that we had. So we worked with blocks of P2O5, and when we used in one plant and in another plant, they reacted in different ways. That's why we had these serious recovery problems and we stopped everything. And when we identified these problems, we said, let's work on these problems. We have not reinvented the wheel. We did what every company did. We dealt with this as if we were starting from zero, from scratch. But we always learn a lot from when we fail, and we were able to redirect our studies to implement this project again. We did a geological mapping of the Domingos mine, and Professor Alex helped us from the Geochemistry University. And we did a campaign for the analysis, complete analysis of the samples. We did a geochemical and chemical analysis and the size of the particles, and we did an updated geological modeling and also directed studies for each kind of ore that was identified. So the greatest key of the Arraias project and why we failed was the insufficient geological knowledge at the beginning of the project. Not because the professionals who were involved didn't have the capacity to do that, but because we discovered many things when we opened the mine. And this happens, right? So the most important point and the changes, we discovered a conglomerate layer in the Domingos mine that was not known. And this conglomerate layer represented a high percentage of the Domingos mine. We didn't have any geochemical analysis of this. We didn't have a flotation study. We didn't have a beneficiation study. We didn't have anything, and we were working with 60% of the volume. The ore was going to the plant without us knowing it well. And so we did analysis, and geologically speaking, we added this to the Santa Fe group. And we understand that this is an important unit, and it has up to 40 meters of this kind of rock. But this is below a layer of soil that is 6 meters deep. And so when we perforated the holes, we didn't have the samples to analyze this when we drilled the holes. And this is the analysis campaign that we did. In red, we have the holes, the recent holes in the Domingos mine, and these are the old holes. So you're gonna find 4 or 5 points in green, okay? And we were able to identify this kind of ore. And starting in 2020, we had 100 meters before, and so the variability of the deposit is high for 100 meters. So we decided to create a grid that is smaller. And we identify 5 types of ores. Phosphated marga, and so phosphated clay and sand siltite conglomerate that became our most important unit when it comes to volume, and the phosphatic breach that we knew it was there, we knew it existed, but we didn't know exactly where it was. So the work that we did recently was to try to identify this phosphatic breach. And this is an important point, and it gave us operational freedom. So the main types of ore that we found. We have the siltite, the sand siltite, the clay siltite is a little pinker. The conglomerate, it has about, it is on top of these layers of siltite, and the main one that we use is the breach. It goes through all of these units, and this is a later event. After this discovery, okay, of these ores, everything became a lot simpler. We characterize all of the samples from a geochemical perspective, and we use some important parameters and something about the conglomerate. Even though the volume is high, the relationship with calcium is not so positive as like other types of ores. So we have some phosphate aluminum. They are not so good for our beneficiation process. Besides that, and another important point was to separate the siltites. The sand siltites, due to the amount of fine particles and its content, this does not help and it harms our beneficiation process. We saw that up until 2019, and this is not a mineral reserve for us when it comes to sending it to the beneficiation plant. So separating the sand siltite from the clay siltite is essential for us. And since we only analyze one part, we're going to try to apply to these geochemical parameters to the entire deposit, and we're going to try to see if it makes sense to use the samples that we currently have. We also carried out some geometallurgical studies, and so we only had that for the breaches and for the siltites, but we are considering them for the sandy parts and the clay parts. And so we lack knowledge, but it has the best recovery when it comes to the concentrate levels that comes from the beneficiation of this kind of ore. It's 28%. And this study was done at Geisa and also in Pennsylvania. And we had the phosphatic breach. It's the best kind of mineral, and we only had a concentrate of 26%. And we tried to get in touch with Professor André from the Federal University of Catalan to carry out these studies, to study the breach once again. I'm going to go quickly through the slides, and then we did a study only for this phosphatic breach, because this breach gave us a lot of operational freedom, and we can produce some kinds of products that the other minerals didn't allow us to do. And we obtained results that are outstanding. And we were able to get recoveries above 90% of the P2O5 in the concentrated minerals, okay? Above 27%. And this was done with the direct samples without the desludging. And finally, our geological model, the final one. So we have the P2O5 without controls. And now we have a very good geological control for this mine. We have the definition. Where is our conglomerates? Where is our clay siltstones? We have the sandy siltstone, and we have it's in the west part of the deposit, so we can we can move away from it, okay? And then we have the contaminants, and the size of the particles is also important. So if you compare the old geological model and the new one, the profile that we had was basically the lime at the bottom, and then the siltite in green, and it was very simple. Now when we compare the current geological models, we have a lithological model at the top, and associated to this lithological model, we have all of the information there based on the current studies that we did. And now we have a huge capacity to start operating again, operating in our mine as soon as we start our beneficiation processes. We haven't started our beneficiation processes yet, but we are going to produce this. Now we have a great idea of the volumes of ores that we have. We have a mining plan. We can do that. And I believe that we are very optimistic now regarding our future for the Arraias deposit. So between 2013 and 2019, Itafos had many operational problems. And we can relate these problems to the insufficient characterization of our ores. Okay, we didn't have the chemical, granulometric, stratified, spatial distribution. so our ROM ore did not correspond to the configuration that we had. Our recovery was lower than expected. So we have now recent studies, and the geology proved to be way more complex. So we have at least at least four main ores. Okay, its magnesium content is very, very high, so it's not very good. So each kind of ore, they have their own physical and chemical characteristics, and we can identify other targets based on their geochemical characteristics. So I can have a more selective mining work, and we can generate different products. So if we want to generate a fertilizer to be used directly, we know what to do. If we want to have a partially acidulated fertilizer, we can do that as well. We can produce SSP from the concentrates that we have with 28% of P2O5. So we know what to do now. And so now the natural finds, their recovery is the greatest challenge that we have now. But in general, this is the story of the project. Okay, thank you very much. Thank you so much. Your presentations are always interesting. And this presentation that we have about what happened, what can be done, and this is very important for our industry. And I wish you all the success in the world. So due to the time, so colleagues, please, if you have any questions, ask the speaker during lunch, or our colleagues from Itafos during lunch.